So thank you very much for the invitation. It's always a pleasure being here at ESI. I've been here like a postdoc around 10 years ago, more or less, even a little bit more. And so probably, I don't know many of you, probably we met in some conferences here and there, and I'm coming from a completely different community, and therefore most likely have a different language and different goals and perspectives to all topics. So I would like to a little bit explain you what is my perspective on the BMS group. To be honest, for me this is like reminding myself how I'm becoming old, because this is what I've been doing 20 years ago. First when I was in Utrecht as a PhD student, and then with Walter Moretti in Trento, and with Klaus Fredenhagen in Hamburg when I was a postdoc. This is like 10 to 15 years ago. And why the BMS group? Okay, so when I was a PhD student, so you know, when you're in Italy, you have to get, of course, interviewed, and the interview at that time consisted in random questions on physics, and then you have to tell the guys what would you do if you get the position. And well, remember that was the year 2001. At that time, everyone just uttered the word ADS-CFT. No matter what, you had to say ADS-CFT because it was super fashionable. And at some point, one guy asked me, okay, what if you're not working in ADS? And suppose you're working in Minkowski spacetime. Do you have a bulk-to-boundary correspondence in Minkowski spacetime? And I said, I have no idea. You know, I just finished my master's studies. Then I went to Utrecht, working under the supervision of Renate Loll and Gerhard Toft as a visiting PhD student. And once more, they asked me, well, actually, mostly a postdoc student of Toft asked me, what about holography in asymptotically flat spacetimes? And I said, I have no idea. I was the first year PhD student, so what should I do? Well, the first thing, nowadays I always joke with my students and my friends, I say, when you don't know what to do, just phone call Walter Moretti in Trento, and then you get an answer. That's, trust me, if you have never done it, do it. He will probably give you the right answer. And the answer was, okay, just start from scratch. Let's say you don't have to look at the ADS-C and try to, ADS-C corresponds and try to mimic it. Just do it on your own from the very beginning. And from the very beginning, he told me, if you have a field theory correspondence, the first thing you need to know is the field theory content of the theory at the boundary. So that's exactly what I did. And then first I did it on my own, and then I started working on this topic together with Walter Moretti and with Nicola Pinamonti. And okay, just to cut a long story short, I will try to explain you how we use the BMS group to infer some information on a field theory in the bulk. Spoiler alert, it has nothing to do with the ADS-CFT correspondence. Actually, it is completely different. It's the total opposite. There is no infrared ultraviolet duality in this framework. Everything will be for this talk. In this talk, it will be concerning free field theory. So there will be nothing particularly fancy, but I will be working on something known as AQFT, or algebraic approach to quantum field theory, which I have to admit is the worst name for advertising. It was good in the 60s. Now they should be changing it completely because it's dramatic. It's if you want to scare people with something which is ultra technical, very far from physics, and mathematically too complicated, then you say AQFT and you have done the job. So I try to convince my colleague one should say, let's say, mathematical approach to QFT would be even better than algebraic quantum field theory. And in particular, will try to explain you how using the BMS group becomes extremely effective in order to construct states. So two-point correlation functions for a field theory in the bulk of an asymptotically flat spacetime by using a BMS invariance on account of the fact that you will be needing a concept which is known as Hadamard states, which is of paramount relevance, as I will be explaining. And unless you have Hadamard states in the bulk, then forget to do anything of what you are used to do in any reasonable quantum field theory. Well, I would rather say that the biggest say, success of this approach, if you want to call it success, has been the fact that we all know that if we work in Schwarzschild spacetime, we have three options, well, not three, but three main options. If you want to look for states of quantum field theory, you can either work with the Boole state, but then the expectation value of your stress energy tensor will be diverging if you take the limit to the event horizon. You can use the Hartlocking state, which is a thermal state in the full space-time, so in the full even Kruskal extension. And the third option is the Unruh state, which is a mixture between a thermal and a ground state. And this state has been, of course, developed with a mode decomposition by Unruh, but it has never been really constructed as a full-fledged two-point correlation function, of which you can prove the Hadamard property, which I will be explaining, is a key concept, at least in mathematical physics. If you want to tell me this field theory you're studying doesn't have any a priori problem. And this was done in collaboration with Walter and Nicola Pinamonti, you see in 2011. And then at some point, we decided to sum up our, let's say, our experience with the BMS group and asymptotically flat spacetime in this book published by Springer. So most likely, if you're interested, I would recommend reading this, which is basically a summary of all we did in the last years. Just another spoiler alert, I will concluding by telling you that at the beginning we had the hope of doing something more than just free fields, namely of working with interacting field theories, but there's let's say the construction we used is not going to work for interacting free field theories, and I will explain you why. It's quite simple, nothing complicated. Maybe there's a way around, but honestly, at that time we didn't know. So let me tell you what is algebraic quantum field theory. Well, algebraic quantum field theory, think of it as quantum field theory in position space. This is basically, if you're not familiar, this is an approach to field theory which is completely equivalent to quantum field theory when you work in Minkowski spacetime. There is no statement, nothing of sort, which is proven or said by any of our colleagues working at CERN, which we will be claiming it's wrong. Everything is completely equivalent. The only point of AQFT is that AQFT has been developed in such a way to be tailored to quantum field theories in curved spacetimes. So you don't know a priori that you are in Minkowski, you want to work in curved spacetime, and there is one thing that I cannot do while my colleagues working for CERN can do is the Fourier transform. If you are in curved spacetime, you don't have isometries in general, and therefore you don't have Fourier transform, and therefore you don't have momenta, and therefore you don't have Feynman diagrams. That's all. That's the beginning of AQFT is mainly this one. You don't know how to work with Feynman diagrams or with momentum representation. I think this was in the 60s, 70s, and 80s. Okay, so the idea of the AQFT is therefore to work as follows. You divide the quantization of field theory into steps. In the first steps, you want to tell me what is observable. What can I observe of a quantum system? Tell me the observables of the systems, and then I would include in this algebra of observables information concerning structural properties, namely equations of motions and canonical commutation or anti-commutation relations. These are the two building blocks that you want to encode in your observer. So tell me which are your observables, tell me how to do repeated measurements, tell me how to implement the CCRs, and tell me how to implement information about the equations of motion. Second, now that you have an algebra which is abstract, then you want to select a state, namely you want to represent your algebra as unbounded operators on a Hilbert space, of which you want to take the expectation value because this is the result of your measurement. So you want self-adjoint operators, you want to have the spectrum, and so on and so forth. But you don't want to choose a priori the Hilbert space because you might be working with the ground state, so working at zero temperature, but you might be wanting to work with, let's say, a thermal bath. For example, you have a field and you want to tell your field, hey, look, there is the cosmic microwave background that, as far as you know, is a thermal bath of photons at a given temperature. These are two completely different informations which entail that you choose two different Hilbert spaces. In one, you have your momenta which are evenly distributed. In the other, you have the Bose, let's say, the Bose distributions. And this has to be encoded in the choice of what is called a quantum state. So as far as standard quantum mechanics goes, this is basically, I'm considering a field theory which is in the Heisenberg representation. There is no Schrödinger picture, there is no interacting picture. We work in the Heisenberg picture. That's the idea of AQFT. Okay, so in the following, I will be considering a global hyperbolic spacetime, which is 4-dimensional. And there is, people claim it's like an old result, but it's actually been proven in 2005 that if your global hyperbolic spacetime is tantamount to being isometric to R cos sigma, it means you have a time direction and you have a spatial direction, so you can set up Cauchy problems by assigning initial data on this hypersurface, so you know what initial data are, and up to an isometry, you can always write your line element as follows, so you have a factor beta and a Riemannian metric, all can be time dependent. For simplicity and not for generality, actually, because I don't want to complicate my life, but I could take any free field, so I will be choosing a conformally coupled real or complex scalar field. This is really not important, and I'm working in 4 dimensions, also this for simplicity. So this is my equation of motion. If you want to add mass, if you want to use spinors, if you want to use electromagnetic, so Maxwell equations, spin 2, whatever, it's perfectly fine. I'm just using this for simplicity. So what is the idea of a measurement in quantum field, in algebraic quantum field theory? Algebraic quantum field theory is the quantization of a classical theory. Therefore, for the first idea is that what is a measurement is assigning a real number to a configuration of a system. So you have here, let's say, your electromagnetic field, and you want to measure some information, say the energy, I don't know, some information on the depointing vector, whatever, about your electromagnetic field. Therefore, you need a map which assigns to each configuration, to each solution of the equations of motion, a real number which you interpret as a classical measurement of your system. This is tantamount to saying that the first thing you have to do when you give me a free field theory is tell me about the solutions of the equations of motion. That's why we work on, well, at that time, we worked on global hyperbolic spacetime. Now we can do it also on asymptotically ADS spacetime. It's just more complicated, but the rationale is the same. So we consider the space of smooth solutions. We smooth functions such that, and this is an important thing, you can represent your solution as the application of what is called the causal propagator to a test function. This might not be familiar to you, but let's see what does it mean. It means the following. So essentially, what you have is that if this is your spacetime and you want to construct a solution, you usually have, let's say, hyperbolic equations. So it means that you have an advanced and a retarded fundamental solution, like you have in Minkowski for the wave equation. So advanced and retarded. And you ask yourself, can I construct all the solutions of the equations of motion out of the advanced and retarded fundamental solution? And the answer is yes, you can. Yes, you can. You can construct them all. And this is because you know that what are the advanced and retarded fundamental solution are both right and left inverses of your equation of motion. So if you want to read it with distribution, this would be the delta. And you know, suppose you would have a compactly supported initial datum, you know that the advanced and the retarded fundamental solution will propagate in the future and the past light cone of an initial datum. Well, if you use a little bit of mathematical theory of distributions, you can say, well, that if you apply to your G plus and G minus what's called a time-like compact function, which is a fancy name to tell you that you have a function which has no support constraint in spatial direction, but it's compact in time. So it is supported inside a time slab like this one. Then it turns out that you can construct all of the solutions of the equation of motion, every solution of the equation of motion, by applying the advanced minus retarded fundamental solution to one of these test functions. And general proof is, general theorem tells you that you want to assign a Cauchy data and solve a Cauchy problem, you want to use the causal propagator, the same. You get as many solutions as you would be doing when working with a causal propagator. So these two ingredients are absolutely the same. All classical solutions, all can be constructed using the advanced and retarded fundamental solution, applying instead of data on a Cauchy surface, you have to apply, let's say, a test function, which is in this case a smooth function, which is just time-like compact. Why one would want to do this? Because one of the key points in the algebraic approach is to keep a manifest covariance at all times. Choosing an initial data on a Cauchy surface breaks manifest covariance because, of course, you have to give me an initial surface. Whereas these propagators, G plus and G minus, are completely covariant because they only know about your equation or your equation of motion, your operator, which is covariant on its own. So that's the first advantage. Of course, your life is not as simple as that because you realize that there are some test functions which are evaluated at 0 by your propagators on account of the fact that since this holds and also the converse, every time you do something like this is automatically 0 because you get h minus h, and this is 0 by definition. So you realize that your space of solution is actually isomorphic as a quotient of vector spaces, which is this one, which you might also discard as an information. We like working with this. Why do we like working with these things? You might say, why? Because algebraic quantum field theory is, for all practical purposes, nowadays not a theory of von Neumann algebras or C-star algebras. We have realized that those things are elements of the past. Forget them. This is a theory of distributions. This is algebraic quantum field theory is a theory where you use distributions to make a rigorous sense imposition space of renormalization, renormalization group flow, perturbative quantum field theory. Everything has been done from the beginning to the end in position space. You can use von Neumann algebras, but it's no longer necessary, and actually it's from time to time quite wrong. Yep. Yep. No restriction. And the reason is causal propagation, because if you want to know the solution here, what is important is only what is causally connected to this point. So of your initial datum, you will only see the intersection between the path-like cone and this. So actually, of your initial datum, you only need the information of a compact part of your initial datum, and that's why you can enlarge the support without having any infrared problem, which one might think to have. Okay, so first thing is that you want to have an observable, and an observable is, let's take it as a map, which reads a configuration of your field. In this case, let's take it as a smooth function. It could be on shell, or it could be not, and spits out either a real or a complex number. Well, there is one very easy way of doing that. The easy way of doing that, if you want to get a number from a smooth function, integrated it against a compactly supported function. So if you take any compactly supported function, this integral is well-defined, convergent, and gives you a number. Does it have any information about the dynamics and the quantum theory? None at all. It's just very, very plain algebra. Yes, but you can implement dynamics. Well, because this is like a pairing. So if you want to tell me, look, when I have a solution of the equation of motion, this has to give 0 because this is 0. This is tantamount to saying that since your operator is a self-adjoint, or actually formally self-adjoint, then this holds true. So you get that the integral of your configuration against P alpha is equal to 0, which is tantamount to saying that if you have an observable of this form, this will evaluate any on-shell configuration 0. So now what you define is, as a basic observable, you say, for every smooth and compactly supported function up to an element of this type, you take a map from solutions into the real numbers, which is defined as follows. So this is just a pairing between your test function and your solution of the equation of motion. This gives you a real number. And one would ask the question, okay, why? I could take anything. Why this? Well, of course, this is not, there's no reason, well, there's no reason a priori, but Occam's razor. So why would you choose this set of observables? The first thing you would tell me is, are there enough observables? What do you mean enough? Well, let's say, using some language from quantum information, how many observers do you want for your theory? The bare minimum is a number of observers which is separating. What does it mean? It means the following. It means, I know you use water, but I am Italian, we don't. This I never managed to learn. So the point is the following: you want to have if you have two observables, one is, why is it separating? Because if for every two configurations, you want to have at least one observable which measures it differently. This is called separating. Like, give me two configurations, there must be at least one observer which tells me these two configurations, these two solutions of your equation of motion, these two electromagnetic fields are completely different. And, well, okay, and this is a separating. If you want fancy theorems, this is a simple consequence of Hahn-Banach theorem, but if you don't, this by brute force method, this is a separating set. A separating set which knows about the equations of motion on account of this quotient. Does it know about quantization? None at all. Next step. Yeah? Yeah, no, because the proper G is, P is in the kernel of G. So if you take this, every solution is written in this form by linearity. But this is formally self-adjoint, and this goes to 0. So it's independent from the choice of the representative in the equivalence class. You don't get a different number. No, for each, you mean for each equivalence class or for each representative in the equivalence class, which is different? For different equivalence classes, you get different numbers, of course. But for two representatives in the same equivalence class, you need to get the same number, otherwise this will be completely ill-defined. That's so different configurations giving you different results, and different test functions give you different results, provided the two test functions are not related by P of something, because in that case, the equation of motions would tell you you get the same result. And this is the information of being on shell. Yeah. This are compactly supported. The observer are compactly supported because at a later stage you want to implement the notion of locality and of being commuting if you are space-like separated, which cannot happen if you are time-like compact or smooth function over the whole space-time. So your configuration is a smooth function everywhere. Like where is the electromagnetic field supported? Everywhere. And so the solution is really supported everywhere. Whereas the test functions with which you define your observer are compactly supported because you want to implement the notion of locality by telling observables need to have compact support. I will get to the BMS. It's just that I think it's, otherwise you will not be getting why I would. Alpha is like an observable. It's like a smearing of, let's say, an idealized observation which happens pointwisely. And then you smear it out and you get something compactly supported. Now, another very bad name. Borges-Ullmann star algebra. Of course, you need to pay respect to those who invented it. It's, if you are familiar with Lie algebras, this is like the universal enveloping algebra. And essentially, it's telling you the following. So now you have your space of observables, which I write here, like here. Let's call E obs M. These are basically all these smooth and compactly supported functions. Okay. So I'm measuring an observable here, but somehow I'm in this room and someone is in the office and wants to measure the, let's say, angular momentum of this particle, and they want to measure the energy of my particle here, and we want to do it at the same time. Nothing has to forbid us doing that. How do you do that? We know for quantum mechanics, you take the tensor product of two observables, telling you can do what you want, I can do what I want, just don't talk with me. That's exactly what the Borges-Ullmann algebra is telling you. Let's take every possible simultaneous measurements of all observables you want in your universe. Fine with me. Do we know about quantum field theory? No, because there is nothing. There's only the information that you're measuring something which is on shell with respect to some equation of motion because of this quotient. Fine. Now, time for quantizing. Quantizing means, look, your field is either bosonic or fermionic since you are in 4 dimensions. If you are in 3 dimensions, you might have anyons or parastatistics. That's also fine, you can do that. But let's stick to bosons. So you want to tell your observables, I'm sorry, you're not commuting. You need to abide by the canonical commutation relations. Therefore, you need to tell you that when you measure simultaneously the observable alpha tensor alpha prime, or alpha prime tensor alpha, this is not the same thing. This is not a commuting operation. The commutator needs to know about the canonical commutation relations. And this is implemented as follows. You need to tell your observable that when you take this minus this minus this is equal to 0. What is this? This is basically this quantity. You take alpha g alpha prime, so you have the propagator here. And now here another problem. Say, look, I was taught that you need to do quantization using the equal time quantization like delta and delta prime, Dirac delta, EH bar delta of x, but this is absolutely the same thing, just at a covariant. I'm sorry that I have to. Because of the following. If you take this propagator, G, this is a distribution, so it has a kernel. And it's something which is, I think, enlightening. Suppose I ask you, how does it look like at time equals 0, so at the initial surface? Well, if you are a mathematician, you're asking, can you do that? Yes, there is a branch of mathematics called microloc analysis, which tells you when and when you cannot do these operations. And it tells you can do that. And it tells you at t equal t prime, this equals 0. Why? If you do the spectral decomposition, you write it in modes, so there is a sign of t minus t prime. So at the initial surface, if you take equal time canonical commutation relations, so t equal t prime, there is 0. But when you derive the sign, you get a cosine, and then what you prove this, which is basically, and then if you go and see, this is when you will be having your fields, this will be telling you that the commutation relations between the fields and the momenta is proportional to the Dirac delta. So you just need to insert an I, which is exactly here, and h bar is equal set to 1, and that's exactly why you can prove that this is a covariant version of the canonical commutation relations. So you need to, now we know what is the algebra of fields. You have to tell your algebra, this is the algebra which knows about the equation of motion, allows for simultaneous measurements, and now you have, by quotienting by means of an ideal, then you're telling your observables you are not commuting, but you might be either, well, you have to abide by the CCRs. On top of that, since alpha and alpha prime are compactly supported, and G has the information that the speed of light is finite, this entails that if alpha and alpha prime are not causally related, that quantity is 0. Observable, which are space-like separated, have to commute. And that's all included in the information of G plus and G minus. So this is a covariant version of the algebra that you would be always using, bearing the fact that we don't have the Fourier transform. So there is no mode decomposition a priori. If you have it, it's completely equivalent. Yet, there is no Hilbert space. And now we are getting close to the BMS. Yes, at this stage, there is a notion of classical limit because I have implemented the canonical commutation relation via formal deformation parameter, which is this h bar. So you can interpret this as a deformation of a Poisson algebra of classical observables. And if you take the pointwise limit, really, of h bar going to 0, you get the Poisson, you get an algebra which is isomorphic to the Poisson algebra of the underlying Hamiltonian system, classical Hamiltonian system. Yes. Yep. It's all classical up to the point that now you have told me that your observables do not commute, because by taking this quotient, I'm telling you that when you take two observables and look at the commutator, this is equal to this quantity, where there is an h bar which I set to 1, is e h bar, this g. So your observable are no longer commuting, but from a strict classical viewpoint, there is no reason why you want your observer not to commute. So they commute. So this information is quantum in a sense that I will specify in the next slide. So up to now, it's a classical Poisson algebra of an Hamiltonian system, which has been deformed in a way which is completely unreasonable from a classical viewpoint. But it's now that I will be recovering the probabilistic interpretation of a quantum theory by assigning a state on top of this algebra that I will be understanding that this has been a quantization of my algebra. Now, up to now, there's nothing really quantum. Yep. Absolutely, yes. This is a yes. Linear observables are left untouched. The deformation happens only at the tensor product. So when you measure simultaneously two observables. But yeah, that's completely left untouched. Okay, what is a state? Okay, here it's something old from the 60s, comes from Gelfand, Nymark, and Siegel. It's telling you, well, suppose you have a star algebra, which is, we have an algebra, star is an involution, and when you can take complex conjugation, it's always an involution. So having a star algebra is not a problem. It tells you, for every star algebra, unital means it needs to have the identity element, which means multiplication by 1. It's not really a big deal if there is no unit, you can add it by hand. It's known to be possible. Then a state is a linear map from your algebra into the complex number, which is normalized, so it measures the identity 1. And for every pair of observable A and A star, it spits out a positive number, which might be even 0. And then for the moment, say, I don't understand. This is the general theorem. It tells you when you have an algebra, star algebra, like the one we have, and when you have a state, then there is what's called a GNS triple, namely up to unitary equivalence, there is a unique Hilbert space, a unique representation of your algebra as linear operator on your Hilbert space, and a unique norm 1 vector called the cyclic vector, which generates the whole Hilbert space if you apply the algebra of observables on top of it, such that the expectation value of your observable on the state omega is the omega evaluated on the observable. If you want to think like this, think of when you're constructing Fock spaces out of creation annihilation operators. If you give me, let's say, the vector 1, 0, 0, 0, so the vacuum on your Fock space, then you can construct the whole Hilbert space, the whole Fock space, by applying creation annihilation operators. That's exactly what this theorem is leading you through. Like, so telling me, you need to give me the Hilbert space. You just need to give me basically how the observables are acting on one distinguished vector, which in quantum field theory, you would call it the ket 0. That's all. Okay, but this is super general, because now you have a generic function which is very, very abstract, and I don't know how to construct it, and I don't know how to get my Fock space. Fine, true, correct. For years, I didn't have an answer, but then the best thing to understand things is to give courses, and then let's not anticipate that, probably, or probably I didn't put it in. Yeah, I put it. Let me show it like this. When you construct states on this algebra, bearing the fact that you have equivalence classes, remember that your algebra is basically like observables, tensor product observables is something like this, no? And I tell you, this is your algebra A, and I want a state on top of this. So I want something which is from this to this, which has to be linear. Okay, linear means that what is an element here? An element in A is of the form Z, F, F prime tensor F2, and so on and so forth. So if you apply this to this guy, by linearity, you can say is omega 0, 0 plus omega 0 F 0 plus omega 0, 0 F prime tensor F2. Okay, this by normalization is Z. This you call the one-point correlation function. This is the two-point correlation function, and so on and so forth. So by linearity and by the form of your algebra, you know that assigning a state is tantamount to assigning endpoint correlation functions, which have to abide by certain constraints, the equation of motion and the CCR. Is this sufficient? Yes, if you assign these things, this is completely sufficient. But on top of that, you want to you consider a subset of all possible states, which are known to be the Gaussian or quasi-free states, which are the states for which the odd correlation functions are 0, and the even ones are completely determined by the two-point correlation functions. And you want to ask me, why should I do that? And the reason is that there is a theorem which tells you that the GNS representation of the algebra fields yields a Fock space if and only if the state is quasi-free. So suppose you don't have Gaussianities, so you don't have a Gaussian state in the universe, then the Hilbert space representation of that state will not be a Fock type. Point. Yep. Mm-hmm. It's the, yep. Absolutely. If you want to think it's like states as smooth so configuration as smooth functions, the dual actually observables are smooth and compactly supported, and states are in the dual of that, so they are distributions. And smooth functions are contained in D prime, but D prime is definitely much larger. And you want it to be much larger, and you want to contain it because you want states to be something which allows for singularities, which smooth function cannot, and you want also to be able to have classical states. So smooth function ought to be inside your set of states. In this picture, it's like that, yes. And on top of that, the problem is that, okay, so for all practical purposes, when you construct a two-point correlation function, you will be needing, if you believe this procedure, you need a distribution on your manifold, which needs to abide by the equation of motions, and the antisymmetric part of your two-point function needs to be your advanced minus retarded fundamental solution, and then positivity of the state is translated in this inequality This guarantees you that the state is positive, so that you have real Hilbert space and not some Krein space where you have to do Gupta-Bloiler stuff. This is really a Hilbert space, and this inequality has a physical significance. If it's equal, then in the Hilbert space representation, you have a pure state. If it's strictly smaller than 0, then you have a mixed state. That's all you need to know. There is, the metric is coming in this guy. Because the propagator is an inverse of the equation of motion, which is a covariant object built intrinsically out of the metric. So that's where the information on the space-time sits. Oh, the Hilbert space. The Hilbert space comes from the state, from omega. Because if you take two observables, let's say A and B in your algebra, you can define inner product in this way, and positivity of the states allows you to prove that, well, you do it in the proof of the GNS theorem, that this is symmetric product in your Hilbert space, which orbits by Cauchy-Schwarz inequality, out of which you can define Hilbert space completion and so on and so forth. So the state has built in the Hilbert space inner product. You have to do some mathematics, but the idea is that the state has the Hilbert space built in. That's why when you're at CERN, if they construct the correlation functions, they know they have a Hilbert space. And that's exactly because of this. Yet, on top of all these states, do I accept all states? Well, and the answer is no, I cannot accept all states. And the reason why I cannot accept all states is because of the fact that if I take all states, then I don't have a covariant notion of Wick polynomial. I want that the ultraviolet behavior of my state is that of the Minkowski vacuum, and I want that quantum fluctuation of all observables are finite. This is tantamount to saying that you want Hadamard states. You don't want Hadamard states, you have to get rid of one of these three conditions. It's a theorem. Hadamard state implies all these three. These three conditions implies Hadamard state. So you don't want Hadamard states, fine, but then you have to get, either you don't have Wick polynomials, so forget about interacting field theories at perturbative level. Wick polynomials, I need, well, in Minkowski would be really normal ordering. In Kerr spacetimes, you need to have a notion of Wick ordering in order to have, let's say, a covariant way of implementing the, let's say, the interacting field theory. And if you have Hadamard states, you can prove that there exists a covariant notion of Wick polynomials, which is completed and constructed out of the metric, and I mean the following. It's the following. Suppose you want to tell me what your field phi squared is. Then if you have a two-point correlation function, this would be defined formally as the integral of the two-point correlation function times a test function times delta of x minus x prime. Yet this product is a product of two distributions, which is a priori ill-defined. And you want to tell me that this can be done, and this can be done covariantly. Well, of course, you cannot do it in general because there are singularities, but you want to make sense of this product by subtracting the singular part of this two-point function in a covariant way. And you prove that if the state is Hadamard, then there is a way to subtract covariantly this two-point function, because the Hadamard condition is telling you that the two-point correlation function in every geodesic neighborhood reads in 4 dimensions as follows, where sigma is the square geodesic distance between the points x and x prime. U and v are smooth functions which are recursively determined out of the equations of motion. And w is a smooth function which is left undetermined and which is your choice in a Hadamard state. So choosing a Hadamard state is choosing this w. Because this part, which is called in mathematical language Hadamard parametrics, is completely geometrical because these two are geometric, these geodesic distances, and these two are functions, u and v, which are completely determined by the fact that your two-point correlation function is on shell. And then you can prove that this is the von Fleck-Moret determinant, which is metric, and this is a power series in sigma, and the coefficients depend either on the square mass of the field or on the geometric curvature invariance, all classified. No, it's a perturbative statement because you're working with distributions which are linear. Non-perturbative states can be constructed only in 2 dimensions, and these are known for example, the Sine-Gordon theory or integrable models. In that case, it's known that the perturbative series converges. On top of that, only in 3-dimensional field theories, you have notion of, let's say, non-perturbative quantum field theory, but this is done in a completely different way via stochastic quantization in the Riemannian setting, and then you prove that you can Wick rotate. But in the Lorentzian, only in 2 dimensions, non-perturbative interacting states are known. This is quantum field theory and Kerr spacetime, no quantum gravity. No, there are attempts, but the point is the following. The big difficulty of these attempts is that at some point you want to say that when you have, say, a minimal length coming from quantum gravity, at some point I would like to have that when you remove this minimal length, then you get something which is consistent with this statement, which is, for all practical purposes, physically speaking, is telling you that if you probe a spacetime with wavelengths which are smaller and smaller and smaller, when you get point to, let's say, 0 wavelength, you're ideally probing a point, and at a point, you can always find a coordinate system which is Minkowski. So I would, yeah, but then one is to tell me that in the ultraviolet behavior, you don't have this. Also because everything we know even about the renormalization group flow of the standard model is built in this. This is also built in the renormalization group flow of standard models. If there is, let's say, a break of this condition, I'm happy, but then I need to be shown that you don't break every result that you get from, let's say, low energy physics at TeV scale. That's something I want to have. About like there's somewhere no very strong requirement that excludes physical phenomena. No. This is consistent with condensed matter physics. Actually, Hadamard and all these things are absolutely consistent with phase transition, adiabatic limit. These have been all worked out. So here, due to the compact support and the fact that you have a reference length scale, you are not in the adiabatic limit. At some point, you want to take adiabatic limits. This has been done. You get thermal equilibrium state, quasi-equilibrium steady states, transition phase, first order, second order. You get everything. You get even symmetry breaking, spontaneous symmetry breaking, Goldstone-like theorems. This is a 1.0 statement. Then you have to go far ahead. No, that's why ultraviolet means infinite frequencies. Because of the fact that it's really the idea that point-wisely you get a Minkowski mate. No, there's no Poincare invariance. Otherwise, no. But for solid-state physics, no, this is like one has to go back to Bratelli-Robinson and operator algebras and quantum statistical mechanics. You are more in the Riemannian setting, so you have to change these things. For example, no, this is for Lorentzian. Yeah, sure. No, then you have to, no, you don't take Hadamard state, then you have to work directly in the Riemannian, and you have another notion of states, which doesn't have this condition because you don't have Minkowski there. And in that case, it precedes AQFT. Like operator algebras in quantum statistical mechanics are by now known to be one possible tool to deal with condensed matter systems, even with parastatistics and all that. So no, this can be adapted. This is strictly Lorentzian. And of course, you want all quantum fluctuation of all observables to be finite. Well, and now, sorry, it's taking long, but I will get to the BMS. There is a notion of state, which is of Hadamard state, which in 1996 tell you that you don't have to look at this condition in every geodesic neighborhood because this is unpractical. You need a tool which is more flexible, which is known as microlocal analysis. The wavefront set, I will not explain you what it is now. If you want, I can, but it's basically a tool to probe singularities of distributions, and it's telling you if a state is Hadamard in this sense, then its singularities are a bit by a certain constraint that it seems very implicit, but actually calculations are very easy in this setting. So let me say you that. So this means the following, that X and Upsilon are related by a light-like geodesic. So they are light-like related. And furthermore, the condition is that Kx and K upsilon are parallelly transported one to each other. But the condition on Kx is that Kx is future pointing, which is, in this setting, the counterpart of the spectrum condition of positive energies that you have in Minkowski, that you say P0 energy positive. This is the same statement in this setting, like positive energy. So you start with a positive energy, singularities are along light rays, so geometric optics, and the covectors, so the momenta, are parallelly transported one to each other along this null geodesic. Do we know that Hadamard state exists? The answer is yes, in many cases. And now the question which I was asked first by Walter Moretti and then by Klaus Friedenhagen was whether you can get states on asymptotically flat spacetimes. And to do this, the answer is yes, we can do that. At that time, we considered asymptotically flat spacetime. I'm sure that here you are more familiar with that, and then I will go quick on that. At that time, we used the Friedrich notion of asymptotically flat spacetime with future time infinity. So this is the standard notion of asymptotically flat spacetimes. After that, we realized it was not strictly necessary. You can relax a lot these conditions. The important thing is that you have something which Ashtekar is calling quasi-isolated horizons, or like we've spoken with Ashtekar, he has this recent paper with Speziale, and I think that our setting applies to that paper slavishly so. This is really what we did at that time, but you can do even more. So let's work on asymptotically flat spacetimes. Then what's important for us is that in a neighborhood of Scry, you get a metric in the Bondi reference frame, which is this one. So this is the Bondi metric. And the Scry is the locus where this capital, I don't remember, psi is equal to 0, whereas the vector d in du is the tangent to Scry, and it's generating a Scry as the light cones which have this vector field as its generator. On top of that, you have the Bondi-Metzner-Sachs group. The Bondi-Metzner-Sachs group is a group of conformal isometries of Scry. So you can take the conformal vector fields of your bulk metric, which become tangent to Scry. And on top of that, the BMS group, it can be proven, or actually it's universal cover to be strictly precise, to be the semi-direct product between SL2C and the smooth functions over the sphere. And you get that U. So it acts as follows. The null coordinate U, which is the coordinate along R, is transformed as follows, where alpha is what you know is a smooth function over the two sphere, and we are using complex coordinates by means of stereographic projections. And these are the super translations, whereas Z, which is the coordinate over the two sphere, is transformed by the action of an SL2C element like this one. So this is just a BMS, standard BMS group in 4 dimensions. Now I am in this situation. Do I get after 5 minutes? Because I know that it's, I just explain you how to build the state. It's not long, but. So the idea is the following. If you are on Scry, and you have observables here, if you get, this is the whole idea you need. This is Scry, and you get observables in the bulk, and then you tell yourself, okay, what can I do with my observables? I have the equations of motion, so the propagator, which is covariant, and it propagates them either to the future or to the past, depending. Let's say here I choose a Scry plus. And then I have my solution, my equation of motion, which allows me to propagate the observables. And then I can read my observables restricted here. So I take F, I take G of F, which means propagate F accordingly to the dynamics of your field, and then restricted it to Scry plus. That's our way of propagating observables to the boundary. So you take an observable, the idea is propagate observables from the bulk to the boundary by using causal propagation. Does it work? Yes, it's not obvious that it works because it's not just propagation. Remember that classically you have an Hamiltonian system. Hamiltonian system has an underlying symplectic structure. The symplectic structure in quantum field theory is encoded by this IG of XX prime. And here you are on Scry, and Scry is a null hypersurface. There is no dynamics because it's characteristic for the wave equation. So the wave equation either propagates here, but on sky, no. Okay, but it's not a problem because on null hypersurfaces, you know how to build, let's say, a symplectic structure which is intrinsic to sky, doesn't know about any dynamics, but it's built in on null hypersurface. This is universal. First and foremost, you have to play a little bit of functional analysis. You construct a space on sky, which it will become useful later. You take smooth functions, which are square integrable, and their derivative is square integrable. And on top of that, you take the following symplectic structure, which is anti-symmetric. And now you know why we need L2 and L2, because if both of these are L2, their product is L1, so the symplectic structure doesn't explode. That's the reason why you want this Sobolev-like space. Fine, then you take this symplectic space as a building block of, let's say, algebra of observables, which is a very bad name. It's of an algebra on Scry, and you mimic what you have done in the bulk. You take S of Scry plus, and then you take the universal enveloping algebra, so all possible measurements, let's say, so to speak, on Scry. And then you tell Scry, look, I have a CCR, well, let's say I have a symplectic structure, so I want the two observables on Scry do not commute, but their commutation is ruled by this symplectic structure. Why this? Because if we prove that this operation from the bulk to the boundary preserves the symplectic structure, which means that this guy on Scry becomes that sigma, then we have proven that causal propagation is sending observables in the bulk to observables in the boundary. Because every observable becomes a smooth function restricted here. I'll tell you, you do some functional analysis, it's L2 with derivative L2. And if you take the commutator between two observables here, you read them on Scry, and it's the commutator on Scry. Yeah? Yes. No, because the Huygens principle doesn't apply on curved spacetimes. If Huygens principle would apply, let's say in conformally Minkowski spacetimes, then you know that causal propagation would be like this, but then you get compactly supported observable on Scry. But here you have what is called in curved spacetime a tail, like your solution has a tail to I plus. And that's why it's not obvious that when you propagate, you get something which sits in this space. In Minkowski or conformally Minkowski, yes. I disagree with him. No, I disagree with him, not because here at the level of algebra, yes, but then I have a state. And then there is the choice of a state, and the state is chosen here intrinsically on Scry. And that's where, so this is half of the story. This doesn't have any memory effect, of course, but that's only half of the story. Exactly. Here I'm looking at the algebra. Well, at this level, of course not, because I have bulk propagation restriction. There should be no memory effect whatsoever. Okay, so how you... Mm-hmm. Yeah. Exactly. So I'm taking an observable in the bulk, and I'm using propagation to propagate to the boundary and read it there as an observable at the boundary. And the idea is that if I push forward observables, I can pull back states. So if I have a state on Scry now, I can have a state in the bulk. By getting a state on Scry, it's much, much, much easier because the BMS group is huge. And therefore, if I ask for BMS invariance, for example, of a two-point function on Scry, then I have one choice. That's... yeah. This has to be proven, otherwise the construction is meaningless. Actually, No, that's why it's so difficult to do it in Schwarzschild, because you need these estimates on the decay of the wave equation by Rodniansky, Dafermos, Blue, and others, because otherwise you don't know whether you sit in this space. So absolutely, it's very, it's not obvious at all. It does apply also to Schwarzschild, this construction. But it variation of, sorry? Oh, no, yes, but the point is, sure. The point is that you can change these spaces. These are not carved into stones. So these spaces depend on the situation in hand. This is a very brutal choice. If you are in Schwarzschild, you have a much more optimal choice. No, this is all true for an asymptotically flat spacetime which has the full scry. So if you have an event horizon, then you have to change it according to that factor, absolutely. Because you have to, so there are some minimal requirements on first and foremost that this is meaningful. Of course, this has to be integrable, but apart from that, Okay, and then, so how you go from the bulk to the boundary, I explained it to you. Well, up to some conformal rescaling, which is necessary, you basically do this operation here. To be precise, here you have to take your f and multiply it by the scale factor of your spacetime to the power -3. Then you go to Scri plus, restrict it, and then you prove that this map, which goes from the bulk to the boundary, preserves the symplectic form. And therefore, this map from the bulk to the boundary is an injective homomorphism of algebra, which means that the algebra of observables in the bulk is mapped into the boundary, it preserves the symplectic form, the star operation, and everything is fine. It's just injective because, of course, in the boundary you get much more. Now, point is that if you send an algebra A into an algebra A prime, then if you have a state here, then you can construct a state for A via pullback, simply. That's the idea. So it means that if you have a state on the boundary algebra, then you can construct a state in the bulk by saying that the pullback, that the state in the bulk is the one which takes on observables, maps it to the boundary, and reads it on the state at the boundary. That's the simple idea. And now, you know that there is a distinguished choice of a state at the boundary, a two-point correlation function, so we look only at the BMS invariant state. You can prove that there exists one BMS invariant state, which reads as follows. So psi prime are function at the boundary, u is the null coordinate, theta and phi now are the coordinate on the two sphere, and this is a unique BMS invariant state. And if you ask why this u minus u prime squared, if you think it's magic, this is not magic, you can think it in two ways. One, it's, since you integrate in u and u prime, this is homogeneous of degree 0. This is homogeneous, so dilation invariant. This is one thing you want to know. Second, if you really like functional analysis, this is the Hilbert transform. So you know it sends L2 in L2. And that's why u minus u prime squared is the right choice. You know that this is L2, but after integration in u prime, it's still L2, and this is meaningful. And this is the unique BMS invariant state. And let me conclude by telling you that at this point, what you have is a state at the boundary. And when you have a state at the boundary, what does it mean? It means the following. I have a state here. And now I have a pullback. And the pullback knows about the metric because the pullback is built of this map upsilon, and this map upsilon has the causal propagator sitting inside. This is and now you have to ask yourself, is it a Hadamard form? Believe me or not, this is super easy now because you have this is very explicit, so you know exactly where it is singular. And then there is one thing in microlocal analysis called propagation of singularities, which is basically telling you that if you have a point where there is a singularity and you have an equation of motion, then if the equation of motion is hyperbolic, all points related to this one and connected by null geodesics will be singular, and you know exactly your singularity. That's what, in lame words, the propagation of singularity is telling you. Mm-hmm. Mm-hmm. Yeah. I think it's, if I'm not mistaken, it's the electric part, but it might be the electric part. By BMS invariance. Because this is the... Yeah, but then you don't have... no, I think you can add the... Okay, so that's exactly why I think that this is like as follows. If you go back to Minkowski, you get the Minkowski vacuum with this state, this for sure. No, but that's one thing. When you have a two-point function, that's what it's correlated to. You can always add something, let's say, brutally. For example, two symmetric product of two solutions or things like this. So you have the freedom of adding something smooth, which does not change the waveform set, which might contain information on the, let's say, on the magnetic part. And that's why I think that memory effect might enter the game, because this is the BMS invariant state with the right singularity, but doesn't mean it's the unique. It's the, here there is a word volume. So it's in the ground state, in the class of ground states, the unique BMS invariant state. So if you allow for excited states or things like this, then you can have others. But this is like, when you go back to the bulk, you are sure that you get a ground state. For example, in Schwarzschild, when you wanted to construct a thermal state, this is not the form of the thermal state. Then you have to change it. This is unique in the volume, which means it's a unique BMS invariant ground state. Yes. No, not necessary. Not necessary. Yes. Yes. Yeah. Yeah, but it will. Yes, but if this means that if you go back to the bulk, this will never be the ground state of that space. That's the statement. So as I told you, bad advertisement. When they say in the volume of, they means if you want a state which is up to unitary transformation, the ground state, or say a KMS state at a given temperature, then it's unique. That's the statement. So it's the unique ground state. It's of Hadamard form, which is what can be proven, and it's invariant under all isometries of the bulk spacetime, if any. And the reason is that this is constructed out of the causal propagator, which is invariant under the isometries. And you know that Killing vector fields are becoming tangent to Scri, and they are generators of BMS algebra elements, and your state is BMS invariant, so it will be invariant under the action of all isometries in the bulk, if any, of course. And in Minkowski, it reduces to the Poincaré vacuum. So the ingredients I already told you. And what is special to asymptotically flat spacetimes, which doesn't apply, for example, in Schwarzschild, and certainly not in Kerr, where it's a disaster, is that you don't have something like the photosphere. The photosphere is something which, where you have light rays ending up at I+. In that case, the proof becomes way more complicated because you have to handle the photosphere not just by looking at Scri, but independently. It can be done, but it's completely more complicated. And I think that here is a good point to stop, since I'm running too much out of time.
Thank you very much.
Yes. In general, at that time, we only looked, if you have both of them, yes, you get, it sits in the form of G plus and G minus. Yes, you can get all these antipodal maps. The point is that at that time, we were interested in the most general class of asymptotically flat spacetime. So in general, you might not have Scri minus. So you might have either Scri minus or Scri plus. That's the reason why I'm considering only one of them, but you can, of course.
Go back and
I'm
what it will be like limit of 5.
So what I think is that you have a choice is, okay, so it depends how you read the memory effect. But here, I would be reading the memory effect here when you have where you have the volume of states. So the point is the following. Let me say it like this. One thing I think, I'm not an expert on memory effect, of course, but yeah, but fine. It will not be, yes. Yeah. It will not be in this space, right? It will not be, if it's not normalizable, it doesn't have finite energy. And therefore, if it has finite energy, it sits here.
Finite energy is that's fine. Finite energy is the norm.
Yeah.
But
Correct. That's okay. So perfectly. This is, and then I tell you how, yes. Now, so if d phi is finite, then this has L2, because yes. Here you can change. No, exactly. But this is, the problem is here that you can prove that this is L1, so it's integrable. This is meaningful. You don't, if it's L2, then it's like textbook computation. But it's exactly what, for example, the same problem that people looking at the stability of Schwarzschild have when they look at the peeling behavior strictly on Scry of their wave equation or on the horizon. They don't have L2. They have a different space. So here they have it L infinity and integrated some other functional space, which means that it's not L2, but still you can prove that this is a well-defined integral. So it's not strictly necessary this to be L1. This one can be L infinity intersected something else. Oh yes, now I remember, sorry. Sorry, but it's 20 years. I have to pretend this has not happened. So this is L infinity, so this has to be bounded. And what turns out is that this one is L2 intersected L1. So it's both L2 and L1. This is enough because if this is L2, you have finite energy. If this is L1, multiplied by L infinity is still L1, and that's integrable. That's how you have to cope. You have to have a little bit less here, which you can have, and more leeway here. So this functional space in Minkowski works fine, in Schwarzschild it doesn't.
this is for the simplicity.
Mm-hmm.
This is where
No, the Klein-God. Infinite and infinite. I mean, yes, because that's a point. That's a point. Like my 2-point function is a distribution. So if you ask me, is the norm of say the representation of an algebra element finite or infinite? My answer is I have no idea. It depends on the case you are considering and on the space-time, because I have distributions, and distributions are much larger. Brutally speaking, I allow for deltas, which have certainly not L2 norms, which are finite in quotation marks. So this object is way more singular than one need. If you want finite energy, then you need to tell me, oh, look, the 2-point function is such that in the GNS representation, it gives you finite energy for your observables. But this is an extra requirement which I've not put here. And of course, it depends on the case you have. So I cannot guarantee that you have finite energy. Finite energy is a statement on being integrable with derivative integral. This 2-point function doesn't know that a priori. You have to add it. No, no, in my opinion, you need to choose other states. The question is the following, which I'm not, I don't know, that you have to tell me this, because I'm not an expert. But for me, there is one thing in, when you take the state and the algebra of observable, and you go to the representational Hilbert space, you always say, I have a Fock space. Or let's say, in quantum mechanics, you have L2 of R3, which is brutally wrong. It's brutally wrong because you have super selection sectors. The real Hilbert space of a free particle in quantum mechanics is not L2 of R3, it's a direct integral over the mass of L2 of R3 labeled by the mass, which tells me the mass is a constant which cannot be changed by any unitary transformation. So if you at some point measure the mass m, you stay with the mass m for the rest of your life. Okay, so my question is, if I choose these, here I am in the ground, so every flux is zero because I have the Minkowski vacuum. But if I change the BMS state by, for example, adding something smooth or things like this, and I go to the GNS representation, I do end up in a different superselection sector, which is tantamount to saying I do end up with different charges. So from my viewpoint, I don't see the need of changing the causal propagation from the bulk to the boundary, but I need to change the two-point function at the boundary in such a way that when I read the Hilbert space representation, which I can do strictly and inherently at the boundary because everything is at the boundary at the end of the day, I might be seeing, okay, my Hilbert space is labeled by conserved quantities which are completely different. If you ask me how to do that, honestly, I don't know, because I've only worked out this one. At that time, we wanted to do interacting quantum field theory with the BMS state. But if I have to read the memory, and that's why I disagree with Abe, is that I think you have much more leeway in choosing this state. This is nice, cozy, and very easy to do computations with, but it's one choice because it's of this. You can add, like he said, the magnetic part, and then you can, when you go to the GNS representation, it's like, say, changing the mass in quantum mechanics, different superselection sector. Honestly not. But I would be interesting to know about this.
I think there's no disagreement.
Yes. 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 Yes, but you know, when we looked at this is, I would say it's here, no, because, yeah, put it this way, when you go at the boundary and you propagate, you just know it's smooth, and then you need to guess, because at that time we were brutal ignorant about functional analysis, and you want to look from here to here, which is the right Hilbert, the right space of functions where you are at the boundary. And if you're coming out of, let's say, a master in physics, and you have not taken functional analysis, that's why I oblige all my students to take functional analysis. It's like, they say, yeah, you can do whatever you want after. And first, functional analysis. You choose L2, and then it's a must. No, because then you realize it, and you don't know in complex system. I've been really uttered ashamed when I was going there with distributions, and people were saying macro-local analysis. I said, why don't you use Bezos spaces? And said, what is that? And then you realize that if you want to do renormalization, the Bezos spaces is way more practical than distributions. But okay, that's another story. That's so here you get L2. This is L2, 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 and L1, and we are happy. But the real point, you see it here, we have proven that in doing this, the algebra is injective. So there is a lot more. So you are in a real small subspace, which means that this is by far not optimal, because if it were optimal, this would, if I would be telling this is an isomorphism, there is nothing to be done. But if it's injective, it means this is the wrong space. And people, for example, Gerard and Michał Wrochna, they have even more complicated spaces using pseudo-differential operators, another tool, and that they show that, for example, they can get rid of this condition and other functional spaces and this is telling you that that our choice was really 1.0 or 0.5 choice. You need to find the correct space at the boundary exactly because of the memory effect. You know that this is not the most general. Yeah. Oh no! That's no. It's super funny. It's super funny. It's super funny because if you go in Fourier mode, so if you do Fourier Plancherel along the u direction, this is you get. Because of this. This is a u 1 over u squared, and you read it as a derivative of 1 over u, whose Fourier transform is the Heaviside function because of this minus I epsilon. So for all practical purposes, think of this as the u of 1 over u. When you do the Fourier transform, you get, well, let's take it. Something like this. So you get the mode decomposition in, oh, this is the Heaviside function. So 1, so it's like the, oh, sorry, I'll do it. No, my bad. So this is, and not to fail my own exam complex conjugation. So the Heaviside function 2k theta k, this is the mode decomposition of the Minkowski vacuum on a constant time Cauchy hypersurface. And the reason is that this u minus u prime is telling you that this is a convolution. So when you go to Fourier transform, the Fourier transform of convolution is the product of the Fourier transforms, this. And on top of that, you get the Fourier transform of the kernel. The derivative becomes k, 1 factor 2 is normalization, and the Fourier transform of 1 over u minus I epsilon is the Heaviside step function, which is basically telling you that you have positive energies. And you see here why it's only in that volume, it's in the ground state, because there is no reason why you should have, if you want a thermal state, this has to be replaced by the Bose distribution. So one way to construct the states on Scry is do it in Fourier space and then Fourier transform back in this way, and then you get the kernel you like. It's much easier, and you don't have to worry about Hadamard condition, because, for example, if here you have the Bose distribution, and you tell me, oh, I don't know whether this is Hadamard or not, there is one simple trick. You know that this is Hadamard. Then if you subtract this with this, or vice versa, and you get a smooth function, which is what you do, then you know it's Hadamard because smooth doesn't change singularities. So you're free to change your, one way to know whether a state is Hadamard is comparing it to the ground state, and then you know that the difference between the 2-point function is to be a smooth kernel, and if it is a smooth kernel, then you have 1.
To free field?
Yes, I can explain.
Like a conceptual big problem?
Yep, it's a concept. Well, I don't know. It is a conceptual problem. To be honest, yesterday when coming on the plane, I was thinking about this problem, and now I'm no longer convinced. It's that if you do some function analysis 3.0, you might get rid of it. But physically, it's quite straightforward. So when you do perturbation theory and quantum field theory, mantra is, and it's absolutely correct, use the time-ordered product. Why? Because if you try to solve nonlinear partial differential equations where nonlinearities are replaced by Wick polynomials, you can use, let's call the perturbative series, Picard iteration, whatever you want to call it, and you have mathematics tells you that you have 4 choices for the propagator. It's called distinguished parametrices. There are 4: advanced, retarded, Feynman, anti-Feynman. You do with the retarded and with the advanced propagator, and you try to do the perturbative series. You hit products of distributions which are singular everywhere, not just on the light cone, everywhere singular, because of the singularities of the propagator. So You do it with the Feynman and anti-Feynman, you have singularities only on the light cone, which tells you that the only thing you can do is work with the Feynman propagator, not because it's like the time-ordered product in quantum mechanics. That's absolutely fine, because this is the only choice to solve a nonlinear PDE in recursively via an iteration schema or a perturbative series. You don't have other choices. You can use the anti-Feynman, but then it's a time reversal. So you have to use the Feynman propagator. But the Feynman propagator, which is in the time-ordered product, has two problems. The first is that this is an inverse of the equation of motion, so it's strictly localized, which is bad. It's bad because you cannot propagate this guy. On top of that, and that's why if you write, the Feynman propagator is known to be related to a two-point function as follows, up to sines. I think it's the advanced. It's I times the state plus the advanced propagator, something like that. It could be the retarded, but it doesn't really matter. So this propagates to the boundary, and we know how to construct to a boundary. This guy I have no, it's strictly localized because it abits by this equation. So at that time, our hope was that we could do interacting quantum field theory on Scry, because there is one thing that you have in quantum field theory, renormalization freedoms. And renormalization freedoms, which are local and covariant, can be proven. It's a theorem that they are completely determined out of the parameters in your equation of motions, so m squared lambda coupling constant, and out of geometric invariance. And the set of independent geometric invariants depends on the space-time dimension. So if you have 4, you have, say, Riemann squared, Ricci squared, so on and so forth, so to speak. But if you go in 3 dimensions, you have less. So our hope was too that we could restrict, like going to Scry, we could restrict the set of renormalization parameters of a theory by doing interactions on Scry, but, well, that's why we failed.
Oh, yeah,
Yes.